All right, one of the things is regarding number 5 here. Sodium is carefully added to aqueous potassium bromide. This one's a trick question. Because the first thing is in the chart method, we inventory it. So we have sodium plus aqueous potassium bromide. Potassium bromide is KBrAq. Now KBrAq is a strong electrolyte, soluble salts. Potassium salts are soluble, so it's going to break up into the ions. So we're going to have potassium and bromide ions present here. And so when we inventory this, this is the inventory. We're going to have sodium metal. We're going to have potassium ions. We're going to have bromide ions. Since this is aqueous, we also have water present here. And then we look at the chart. You know, for example, sodium is a reducing agent. It's on the lithium side. Potassium is an oxidizing agent, ions, potassium ions. Potassium ions is on the fluorine side. The bromide is on the lithium side, so that's a reducing agent. Water is on both sides, so this is both an oxidizing agent and a reducing agent. Then we look, which one is the strongest oxidizer? Is it going to be potassium ions or water? And so we'll go back to the chart and then take a look here at the chart. When we look at the chart, it looks as if water is the worst oxidizer because it's at the bottom of the chart, but these are two charts. And so it looks like water is the worst. It's at the bottom, but it's not. It's minus 0.828. Minus 0.828 means we place it right here. It belongs right in here. And so if it belongs right in here, this is why I drew these 3 dots here. This is where water is. So what that means is water is a stronger oxidizer than aluminum ions, but a weaker oxidizer than zinc ions, you know. What's the other oxidizer? The other oxidizer is potassium ions. So when we look at potassium ions, we have potassium ions here and water up here. And so it turns out that water will be the stronger oxidizer. It's a stronger oxidizer than potassium. Fluorine's the strongest, which is up here out of view. Okay, then we do the reducers. The strongest reducer is at the bottom here, which is lithium. And so we're comparing sodium metal with bromide. And so here's sodium metal. It's very powerful reducer. Where's bromide? Here's bromide. And so sodium metal is more powerful than bromide. And so sodium metal is our reducer. And then we copy the half reactions here. So for sodium, we have to go backwards because it's the we always have to reverse the reducers. And so the reducer is going to be this. Sodium metal goes to sodium ion plus an electron. Sodium metal goes to sodium ion plus an electron. Then we look at the oxidizer. The oxidizer is water here. And so we'll just write it down. 2 waters plus 2 electrons yields hydrogen gas plus 2 hydroxides. Now, what we want to do at this point is we want to use the conjugate relationship. The conjugate relationship goes like this. If this is my reducing agent, this is its conjugate oxidizing agent. And if this is my oxidizing agent, this is my conjugate reducing agent here. And so this helps us label the driving force for later. Okay, now we combine it. But when we combine these two, you could see that the first one here produces 1 electron. The second one consumes 2 electrons. And so the first one here, we're going to have to multiply by 2. Otherwise, we're not going to have enough electrons. And so 2. And then when we do that, we're going to get 2 sodiums, solids. Okay, then we'll add everything on the left, plus 2 H2O, liquids, plus 2 electrons. And then add everything on the right. This is going to produce 2 sodium ions, plus 2 electrons, plus H2 gas, plus 2 hydroxides. Now the electrons have to cancel. So 2 electrons on the left cancel 2 electrons on the right. They have to cancel. And then I look for the driving force. When I do the driving force, I just label it like this. You know, sodium is my Ra, water is my OA, and then sodium ions here, this is my conjugate OA, and H2 and hydroxide, this is my conjugate Ra. And so let's compare the two oxidizing agents. What's a better oxidizing agent, water or sodium ions? And so I look, here's water, and then I look for sodium ions. Here's sodium ions. And it looks like water is a better oxidizing agent than sodium ions. So we're going from stronger oxidizer to weaker oxidizer. And then I look at the reducers, sodium metal versus hydrogen in hydroxide. So here's sodium metal, where's hydrogen in hydroxide? And so I look, hydrogen and hydroxide. Here I have hydrogen, but I'd like hydrogen and hydroxide. Do I see it? Yes, I do see it. It's here. Sorry. It's here, and it should be right there. So hydrogen and hydroxide is here, which is better than hydrogen alone. And so and water's here. And so I see that sodium is better. And so this sodium is stronger, and hydrogen and hydroxide is weaker. Hydrogen and hydroxide I had to add in here because this gets inserted. This whole equation gets inserted right here. So we're gonna make a new row. All right, so what that means is we're going from strong, strong to weak, weak, which means we have driving force. So the reaction is not between the KBr, this is a spectator. This doesn't even participate in the reaction. Water participates in the reaction here. Okay, so that's what we do. Now, not everything comes out on the chart. There's things that aren't going to be on the chart. And so what I need to talk about, this is the last thing I need to talk about, but what we're going to do is, even if you didn't finish this, you know, even if you didn't finish these redox problems, chart ones, can you upload what you have? I need to see what people are doing, you know. This is just participation. So these are going to be points for participation. You don't have to have the right answer, but I want to just see, you know, where people are making mistakes so we can go in and correct those. Okay. And so when you get a chance, upload what you've done, or you could upload it as a group, you know, group work is fine, or upload it individual if you did it individually. But just upload what you've done so I can see if you're on the right track, or you need some kind of course correction to get back on the right track, okay? And so when you get a chance, do that so I can see where you're at. Now, some of the things aren't on the chart, but we can figure those out. And so this is the last thing I want to talk about, and for redox. And so the last thing I want to talk about for redox is the skeleton redox. And so let me talk about that. In skeleton redox, we kind of have an idea of what's happening. You know, we have an idea of what it should be going, but we just don't have the half reaction. Those are called half reactions, you know, what we're looking at. That's a chart of half reactions. And so for skeleton redox, if we know kind of what it forms, we can figure it out using skeleton redox what the complete half reaction should be. And so let me give you an example of this. For example, ethanol is not on the chart, but we saw ethanol is a powerful reducer. You know, it combusts very violently in those reactions with liquid oxygen. And so if we look at ethanol, sorry, probably can't read it very well. We know when we burn ethanol, what does it burn to? So if you completely combust something, do you know what it forms? Does it form carbon monoxide? Does it form, what does it form when you burn something? And so this is what's observed. When we burn things like hydrocarbons, wood, this type of stuff, we form CO2. That's it. We don't form CO3. We might form carbon monoxide, but you know, when they're burning that rocket, it was in pretty intense combustion. So what we're gonna do is we're gonna assume we have complete combustion. Complete combustion is gonna form CO2. And so this is what we call a skeleton redox. This is called a skeleton half reaction here. All we know is that ethanol is probably going to burn and it's probably going to form CO2. That's what's going to happen. And so if we want to know the whole thing, the whole story, then this is what we do for skeleton redox. So this is skeleton half reaction. To complete this, there are steps to get the complete half reaction. And so determining the half reaction would be what we'd use from the chart. This one doesn't occur on the chart. And so we're gonna figure it out. And so we have CH3, CH2, OH, and that's going to eventually go to CO2, you know, when it burns. And so step one, or we'll call it A. Okay. Step A is we balance all elements except H and O by changing coefficient. And so in this case, we have H, O, and C. So the only element that we have that's not carbon and, that's not hydrogen and oxygen is carbon. And so we have 2 carbons on the left. So I'm going to write 2 carbons, 2 C's on the left. On the right, I only have 1 C. And so what I'm going to do here is I'm going to change the coefficient. And so let's do that here. I'll just do it a different color here. And so what that means is I'm going to change the coefficient here to 2. And so now if I have 2 CO2s, I'll have 2 carbons. And so the carbons are balanced now. I've got 2 carbons on the left and 2 carbons on the right. Okay, that's A. Now we go on to B. Step B is we're going to balance the oxygens. The way we're going to balance the oxygens is by adding water. And so I'm going to go over here for B. Balance oxygen by adding water, H2O. And so how many oxygens do I have on the left? I have 1 oxygen on the left. And then I have 2 times 2 is 4 oxygens on the right. And so I need 3 more oxygens here. I can't change the coefficient. That's going to screw up the carbons. I can't add O because there's no O here to begin with. What I have to do is I have to add H2O. Well, H2O is usually present in a lot of these. So here, what I'm going to do is I'm going to add 3 H2O. Like that. And so now I'm going to have 3 plus 1 is 4 oxygens and 4 oxygens. So the oxygens are now balanced here. Checks out. That's B. Now let's go on to C. The next step is we're going to balance the hydrogens. Balance H by adding H plus. And so when I look at the H's here, on the left, let's count all of them, including the waters. And so I have 3, 4, 5, 6 plus 6 gives me 12 H's on the left altogether. On the right, well, CO2 doesn't have any H, so I say there's 0 H's on the right. And so I need to add 12 H pluses to the right side. And so over here, I'm going to do plus, oops, wrong. Try that again. This is going to be plus 12 H plus. Here. And so that's going to balance out the hydrogens. Okay, then finally, there's only one more step to this. The last step is we'll call D. And D, we're going to balance the charge by adding electrons, by adding negative charges. So electrons are negative charged here. And so ethanol is neutral, water is neutral. So the charge on the left is 0. When I look at the charge on the right, CO2 is neutral, but H plus is positive, and I have 12 of those. So I have plus 12 on the right. And so what I have to do is I have to add negative charges until the 2 sides match. It doesn't necessarily have to go to 0 on both sides. It just has to be matching. So if it's plus 12 on the right, it better be plus 12 on the left. Then it's matching, and we're okay. In this case, I'm going to bring both of them down to 0 because it's the only way to get these to work. So I'm going to add 12 electrons, excuse me. And that should cancel out the plus 12 here. And so altogether, this is going to be ethanol, CH3, CH2, OH, ethanol, plus 3 H2Os, liquids. This is going to produce 2 CO2 gas plus 12 H plus 12 electrons. So here, this is a reducing agent, you know. This is a reducing agent because it's losing electrons here. The conjugate oxidizing agent would be this. If we went backwards, this would be the oxidizing agent going backwards, gaining electrons here. Now, okay, so this would be a balanced skeleton half reaction. We got to check it's balanced. And so it's easy to make mistakes. So when we check that it's balanced, okay, so E, do that. E, check atom and charge balance. Check atom and charge balance. And so this is a double check here. Checking atom balance, I have 2 carbon atoms. On the left, I have 2 carbons. On the right, I have 3 plus 2 is 5, plus 1 is 6, plus 6 is 12. 12 hydrogens on the left, I have 12 hydrogens on the right. Then I have 1 oxygen plus 3 oxygens, 4 oxygens on the left, I have 4 oxygens on the right. So the atoms are balanced. Then I check the charge. The total charge on the left is 0 plus 0, 0. 0 plus 12 is plus 12, minus 12 is 0. And so the charge and atom balance checks out. And so this is the reaction. So if there was room on the chart, they would have included this. If there was room on the chart, they would have included this. Now, we can use any oxidizer to oxidize this. And so, for example, we could use, let's pick one oxidizer. We could use oxygen to oxidize this. Here, oxygen. And so if we choose oxygen, then we have this one, oxygen plus 4H plus, let's see, 2 H2Os minus 2 plus 4 electrons yields 2 H2O liquids. And so we could use oxygen as the oxidizer here and then combine these two half reactions. So this would be an example of this particular reaction here using this. And so here, this one's gaining 4 electrons. This one's losing 12 electrons. And so this one, I need to multiply by 3 to get the electrons to match. And so let's, let me do some erasing here. But I could use other oxidizers as well, you know, to do this. So let's just use oxygen because that's what they used in the video for the NASA rocket. But they use liquid oxygen. This is going to be gaseous oxygen here as the oxidizer. And so when I combine these two, I'm going to have to multiply these by some number so that the electrons match. Here I got 12 electrons, I only have 4 electrons here. And so in this particular case, I will multiply the top one here by 3. So that gives me 3 oxygens, 12 H plus, 12 electrons. Okay, balanced charge by, okay, what does party say? Okay, sorry, I missed these here. Yeah, I'm gonna put it up on Canvas right after class. I'll put a place where you can load it. I'll probably end a little bit early today. And so, okay, what we're gonna do here is we're going to add these. Combine them. So I'll combine everything here. So combining these two, I'm going to get 3 oxygens plus 12 H plus. Yeah, I better not do red in case there are issues with the color. 3 oxygens plus 12 H plus maybe this is even worse, plus 12 electrons. Okay, that's everything on the left, plus everything on the left here, plus 1 ethanol, H3CH2OH, plus 3 waters. Okay, that's everything on the left here. And now let's combine that, everything on the right. So everything on the right is 3 times 2 is 6 waters. And then everything on the right here, this is plus 2 CO2s, plus 12 H plus 12 electrons. Now, what we're going to do is, for driving force, the easiest thing to do is based on the half reactions. Based on the half reactions, O2 and H plus are taking electrons. So this is my oxidizer, and therefore this is the conjugate reducer. Over here, ethanol and water, that's losing electrons. So this is my reducer, and therefore this is my conjugate oxidizer if I went backwards. And so I can do this quickly. This is going to be my oxidizer in the forward direction. This is going to be my reducer in the forward direction. In the reverse direction, water here is my reducer. So water is my reducer, and CO2 is my oxidizer. CO2 and H plus is my oxidizer. And so here, CO2 is not on the chart, but we know from experience, what's a better oxidizer, O2 or CO2? You know, what's a better oxidizer, O2 or CO2? O2. And so just based on experience, we say we're going from stronger to weaker. What do you think is easier to burn? Ethanol or water? What's easier to burn, ethanol or water? With an oxidizer, what's easier to burn with an oxidizer, ethanol or water? Oh, this should be pretty obvious. Ethanol. Ethanol is a heck of a lot easier to burn than water. You think NASA is going to make a rocket engine burning water? No, probably not. Not with this kind of reaction. Now the 12 electrons have to cancel, which they do. And so there's driving force here. Now what we're going to do is we're going to simplify. Simplify because we can get rid of or cancel some of the stuff on the left and the right. And so I'm going to simplify this by saying, okay, I have 3 O2s, but I have 12 H plus here. I have 12 H plus here. Let's cancel out the 12 H pluses. 12 H plus here cancels out 12 H plus here. I have 3 waters here, and I have 6 waters here. So let's cancel out 3 out of the 6 waters. And so the net reaction here, after I cancel out, things, I'm going to get 3 O2 gas plus ethanol, C3, CH3, CH2, OH, yields 3 H2O plus 2 CO2s. So this shows combustion. When we combust alcohols, we form CO2 and water. In fact, when we combust, like most hydrocarbons, in fact, all hydrocarbons, we're going to get CO2 and water, as long as some hydrocarbons have other elements present, like nitrogen and whatnot. And so those will lead to different products. But this is what we're going to, ethanol is liquid. And so this is using the half. In Chem 4, though, for combustion reactions, we just usually do it in this way. I didn't do combustion here. But in combustion reactions, it's like combustion analysis. We take a hydrocarbon, CXHY, this is from the last chapter, I think, and react it with excess O2. When we react it with excess O2, we form CO2 and water. So we probably could have figured it out here. But the situation is, oxygen is only one oxidizer. There are lots of different oxidizers. So we don't even need oxygen to burn ethanol. We could use other oxidizers to burn ethanol. And so in the complete absence of oxygen, we could burn ethanol. Let's see what time it is now. Okay, it's 6. All right, so I'm going to stop here. I'll post a link on on Canvas. So just turn in what you have so I know, you know, what to talk about on Monday. And then we're going to finish up this redox, and then we're going to move on to the two other types of reactions, metathesis and acid base, for the first part of class on Monday, and then the rest. I know you guys are working on the exam, so you don't have to have this complete. Even though this is worth points, it doesn't have to be complete. Just turn in what you have as a participation quiz, okay? All right, so I'll post the link. Anyway, have a nice weekend, and good luck on the test. I'll see you guys on Monday, and the test is due Monday, all right? Okay, any questions before we end it? All right, thanks. Yeah, great. Okay, see you guys.